Welcome back. So last time we talked about work transfer as a form of energy transfer across the system boundary. Now there are a few key points we need to remember. Work transfer is not a system property. Work transfer depends on the process path, and there are many different types and forms of work transfer. So last time we introduced expansion and compression work, and that's the work to raise or lower a piston. Now that type of work is very important because that's pretty much the power generation that's used in all of the transportation sector, is expansion and compression work. And so we looked at that as a specific example, and then we left with the question of what would a constant pressure compression process look like on a pressure volume diagram. So we're starting to put some of our tools together. The PV, pressure volume diagram, are state diagrams. We're going to discuss those quite a bit in the coming lectures. But we also talked about work as being, in its most general form, an integral expression. And then we said, okay, there's a specific form of that expression for expansion and compression work. So let's answer that question now. Okay, so we talked about the PV diagram. And again, we said that work in its most general form could be expressed as an integral moving from one state condition to a second state condition. So that's S1 to S2. And the most general form of that expression is one where we use just some force times the distance that force is executed in that process. So from state 1 to state 2, force integrated over that distance, over that process distance. And we said for expansion and compression work in particular, we would move from state 1 to state 2, and that the form of the expression was pressure times the differential d volume. So remember, the V with the crosshash is a volume expression. Okay, so that's our expression. If we have a constant pressure process, we know that that pressure is constant, and we know from our math that we can take the pressure outside of that integral. The state conditions here are now volume at state 1 and the volume at state 2. So integrating that expression is pretty simple now. Right? We have the work is simply equal to the constant pressure times the volume at state 2 minus the volume at state 1. Okay? And I like to keep track of our state conditions, our process path, by using the notation 1, 2. So we're going to say we start at state 1 and we end at state 2. So now we come back to that question. What does constant pressure compression look like? Well, it's constant pressure, so we know that's going to be pretty straightforward. It's a straight line. And we know that we have an initial state and a final state. We have to decide which is which on this diagram. So we know it's compression, so we should start at a higher volume and end at a lower volume. And we know to emphasize that, we'll give an arrow to show the direction. So that's supposed to be a straight line there. But that's what constant pressure compression process would look like on a PV diagram. Cool. So hopefully that was pretty straightforward for you. Now, like I said, there are lots of other forms of work. And which form of work is relevant to the problem we're considering depends on the problem itself. So we're only going to define in detail one more, and that's shaft work. Shaft work is the work that we use to generate power by rotating machinery. So all of your jet engines, your gas turbines, any type of turbine generates work by spinning a shaft. There's also extension work. That's when you might extrude a metal or pull on a piece of plastic. Electrical work we sort of use. Electrical work is, of course, the power. Generally, we consider it power instead of energy transfer. So it's energy, the rate of energy transfer. But that'd be like if we plug in a television set, for example. The energy that takes, that energy transfer process it takes to power the television is electrical work. So we don't tend to look at the details of the electrical work in thermodynamics. We just take that as an input condition. And we recognize that it's electrical work. There's also film work and many other types of work. That'd be like if we were looking at something like a plasma, like we would find in a fluorescent light bulb. We would have to consider these different forms of work. But again, for the big primary sources of power in the transportation, stationary power sector, in your home, all those types of work are really going to be covered by shaft work, shaft work, compression and expansion work, and electrical work. So let's take a look at shaft work real quickly. Again, because we want to understand that one because it's the primary way we generate power in the stationary sector. So in a shaft system, we have something that's rotating. And again, if we were looking at a turbine, these would be the turbine blades or a compressor or pump or anything that has rotating machinery like that. So forgive my artistic rendering here. But what we want to show is that we have a shaft that carries transfers that energy, and it's rotating. And so we go back to our general description of work is equal to the force times the product of the distance that it's executed. And in this case, the force that's executed is a tangential force because we have a rotating piece of machinery. And so we define that as a tangential force. And more specifically, we know that that velocity at which we rotate is given by the product of, this is a, I'll try and make this a script W here so we can understand that that's actually the angular velocity of that shaft, and R, of course, is the radius. And we're going to take that velocity, so this is a velocity, but it's a radial velocity here, at the point of application of that tangential force. Okay, so if we put that together, and now I'm going to introduce another term here, or at least a form of an expression. We're going to take that W and we're going to put an over dot on that. And that is always going to mean that the variable is on a per unit time basis or a rate basis. So this means rate basis or per unit time. Okay. And after we go through that exercise, I'll use a script T here to denote the torque. We find that the power generated for a shaft is simply the product of the torque times that angular velocity. Okay, so again, that's the only other work term that we're going to care about in detail in terms of the expression, because we want to know typically how to correlate the angular velocity with the power out of the system. So let's review. We talked about sign conventions in the previous lecture too. So what does that mean? Work out of a system is positive. So that's greater than zero, where our work term here would be greater than zero. And that's considered, the phrase we would use is that work is done by the system. So my turbine, if it's generating power, which we kind of hope all turbines are generating power, that would be work out of the system. It would be a positive term. If the work is into the system, like when we compress a gas like we would use in it, like we do in an engine, then that term is negative. That would give us a numerical value less than zero, and the work is done on the system. Again, this is a traditional sign convention for thermodynamics, and it's not uniform. So you go to other disciplines, and you'll find different sign conventions. So one of the first things you need to understand when you're reading somebody's analysis or when you're doing your own analysis is what's the sign convention you are going to use. And it's your discretion. You can use a positive sign convention for positive workout, or you can change that around. But you have to be consistent. And in this class, this is the sign convention that we're going to use. So you have to consistently use this sign convention. So I already gave you my speech about units. The units should always help you in your analysis. The sign convention should always help you in your analysis. So just remember your sign convention, be consistent, and it will be a tool to help you understand how your system is behaving. Okay, so this should be easy now. If a turbine generates power by shaft work, what is the sign for the work done by the system?